Good afternoon.
Hello guys, nice to see you.
Good afternoon.
Hi, how are you doing?
Not bad. What about you?
Also good, yeah. Could be worse, so cannot complain. Okay. Good afternoon. Yeah, so short summary of our previous discussion. We considered the derivation of equation which quantifies the speed of wave propagation. Oh, yeah, sure, we can wait for 1 minute. But I mean, it's not something new, some new material. I just want to summarize previous discussion. So that's why I believe it's not so critical. We will start new material a bit later. So we derived this equation for the speed of wave propagation and considered few phenomena which happens at the interface between two medium with different speed of wave propagation. So we should take into account from which medium the wave is approaching the interface, because the reflected wave will possess either the same or opposite phase, depends on the fact either speed of wave propagation in the first medium is higher than in the second, or in the contrary. So that you should please keep under consideration. Also, there was a question at the end of the previous discussion regarding the amplitudes in the reflected and transmitted waves. Somehow I was considering the incident and reflected wave when attached firmly to the wall. So then if there are no energy losses, then the amplitude of incident and reflected will be the same. Lesson which was on Wednesday. Yeah, I will post today both because I was busy and didn't have time to post them immediately. So there will be both lectures from previous time and from today. Yeah, so the thing is that the amplitude, so the correct answer to this question regarding transmitted and reflected waves. So their amplitudes will not be equal if we have two different environments, and that will be defined by the ratio between the speed of wave propagation in one first medium and in second medium. So if I change my screen now and write you two equations which will determine the amplitudes of transmitted and reflected waves. I hope it works. Yeah, okay, it works. Last time it didn't work for my previous, from other session. So we can write, if we consider AI as amplitude of incident pulse or wave, then reflected amplitude will be defined by the following equation, will be V2 minus V1 divided by V2 plus V1 times AI, and the transmitted wave will possess amplitude AT, which is equal to 2 times V2 divided by V2 plus V1. And here we have AI. So in terms of initial incident amplitude, we can determine reflected and transmitted amplitudes based on the ratio between the speed of wave propagation in the first and second medium. And obviously, first and second will change, depends on from which medium the wave is approaching the interface. So yeah, last time I was confused and was considering this incident and reflected wave from the firmly fixed edge of the string. Then amplitudes are the same if we consider no energy loss. However, with this transmitted and reflected waves, we have some certain distribution of values for amplitude based on the ratio between these two mediums, based on the ratios of the speed of wave propagation in these two mediums. Okay, so now we can proceed further, and our goal for today is to derive equations for energy transferred by wave in, let's if we consider, for instance, some wave on a string as a model for consideration, and also power means energy per unit time. So our goal to derive these equations and understand which parameters will define energy transferred by the wave. So for this,
sorry, could you please repeat? There is a bad internet connection.
So today our goal is to derive equations which will calculate the energy transferred by the wave. So we will consider some wave propagating on a string, and we will figure out which parameters define how much energy per unit time is transferred by such a wave. So that is the purpose of our today's discussion. And as an example of fact that wave or some mechanical disturbance in the form of a pulse carry some energy, we can consider such case. Let's say we have some pulse moving from the left to the right. Here it is fixed. And here we have some block attached to this string M. So this wave is coming closer to this point where block is attached. And in that moment, when it reaches this location, this element of the string where the block is attached will move upwards. Means that this pulse will perform some work in moving the block with mass M upwards against the gravitational force. So obviously, mechanical waves, they carry some energy, and our goal is to quantify it. For this purpose, we need to consider some convenient model for our derivation. And the best example would be if we consider some simple harmonic oscillator. So let's say we have some simple harmonic oscillator attached to a string, and then it vibrates and creates a mechanical wave moving along axis X, and elements of this string, they will move up and down along axis Y. So now let us consider some small element of this string, which is dx, length dx, and mass dm. So let us focus now on the kinetic energy of the this element of the string. So kinetic energy, we know, is defined as 1/2 times mass times v squared. So we consider this speed v along axis y, because we remember that displacement of any element of the string happens only in the y direction, up and down, and elements of the string do not move along axis x. Only energy is transferred with the wave along axis x, but elements of the string oscillate, they experience some displacements only along axis y. So we can write for this small element dm that its kinetic energy, let's call it dk, will be equal to 1/2 times dm times v y squared. So let's put it y here just to highlight that this speed is along axis y. So now we have this dm, and we need to express it in terms of dx. So we assume that there is some linear density distribution, which is constant. So it doesn't change with along the string. And with this, we can write that dm is equal to mu times dx. And then we can substitute it in our equation for kinetic energy. That will be 1/2. Instead of dm, we have mu times dx, and here will be v squared. I don't write y anymore, just we don't need it. We already know that this is along axis y. So from our previous discussions, we have shown that based on this equation, which defines displacement as a function of position and time, if we take first partial derivative dy over dt at x equals constant, we get the speed along axis y with which each element at position x, at any arbitrary position x, will move. So we did that previously, and that's why we can just write the equation which we derived. It was minus omega times a times cosinus kx minus omega t. In general, it's plus phi initial phase, but we can consider that phi is equal to 0. So then we can substitute instead of v this expression, and we will get the following expression. dk is equal to 1/2 times mu. Actually, it would be good to split now dx because we need dx at the end. So let's write here just mu times, instead of v, we have minus omega a cosinus kx minus omega t. This is in second power. And here, so this expression stands instead of speed. Here we have dx. So we can write that this is equal to 1/2 times mu. Since we have second power, this minus will be gone. So we will have omega squared times a squared times cosinus square omega t. Sorry. Let's write it first. So multiply cosinus square kx minus omega t. And here will be dx. Okay, now next step, since we want to deal with distance, we have this dx here. We need to get rid of time, means we need to consider at some moment of time this function. That's why let us consider t equals 0. So then our function will define kinetic energy of small element of the string at any position along axis x at given fixed moment of time, t equals 0. So taking that into account, we can rewrite final equation. Let's do it on the next slide. So that will be dk will be equal to 1/2 mu omega squared times a squared times cosinus square. Here will be kx without minus omega t because t is considered to be 0 times dx. So now we need to do the next step and consider kinetic energy at the distance interval of one wavelength. So if we come back to the previous slide, so here, for instance, let's consider that here is x equals 0. Then we know from definition that wavelength is the distance between two adjacent points on the wave, which are in the same phase, like two closest adjacent points. So means that wavelength is defined by this distance, it's lambda. And what we want, this wavelength distance along this distance lambda, we have many small elements of this string. And if we want to know kinetic energy of all of them, we need to integrate our expression from 0 to lambda. Along axis x, we have this dx in our expression. So let's call this kinetic energy per unit wavelength k lambda. That is equal to integral from 0 to lambda integral from 0 to lambda dk. Now let us substitute all this equation. So it will be integral from 0 to lambda okay, maybe better let's take out from integral all our constants. We have a bunch of them. So actually all guys here are constants. So we don't need them under our integral. So that will be 1/2 times mu times omega squared times a squared times integral from 0 to lambda times cosinus square kx dx. Okay, now any ideas how we take this integral? Cosinus square kx dx. There should be some trigonometric transformation because otherwise we will not be able to simplify it to this table of integrals conditions. So we can
Maybe
write.
we should somehow lower the factor of cosinus.
Exactly, you are absolutely right. So
there was a formula, I believe, which said something like cosine of 2x plus 1 divided by 2. It was something like that, I guess.
Yeah, something similar. So yeah, it's actually this equation. You are right. So cosine square x can be expressed by 1 plus cosine 2x divided by 2. So if we consider this expression, then it would be much easier to integrate. So let's keep this in mind. Let's maybe write like this. We can delete this part. Then it will be equal our constants 1/2 mu omega square a square. Then we have our integral from 0 to lambda. And here we will have not just 2x, but we have kx. So it will be 2kx. It will be 2kx. And here we have dx. Okay, now after this transformation, we can split this integral in 2. So let's again write our constants. Then we have first integral, which will be 1/2 integral from 0 to lambda dx x plus 1/2 integral from 0 to lambda cosinus 2k times x dx. Okay, so first integral is very simple. So that will be 1/2 mu omega square a square. Here will be x divided by 2 from 0 to lambda. And the second one, we actually need to do some changes here. So we see that in the argument of cosinus, we have 2kx. So we want to have the same differential, not just dx, but d2kx. Since these are constant 2k, so we can just multiply and divide this integral by 2k. So 2k will go to the differential, it will be d2kx, and another will be here, like 1 over, in front of integral, 1 over 2k. So it will be 1/2 times 1 over 2k, integral from 0 to lambda, cosinus 2kx d2kx. So now we can easily integrate this. So let us maybe go to next slide. We write here our, maybe let's start from k lambda to be sure we remember what we are calculating. Equal. So here are our constants, 1/2 times mu times omega square times a square. Then we have lambda divided by 2. If we substitute this interval already to the first integral, then plus 1 divided by 4k. Integral of cosinus will give us sinus. So it will be sinus 2kx from 0 to lambda. And finally, we will get 1/2 mu omega square a square. Lambda divided by 2 plus, so we substitute these intervals. So it will be 1 over 4k times sinus 2k times lambda. Okay, so we got this integral, and now we need to get the final expression for our kinetic energy per one wavelength. The question is, any ideas what this term will be equal to? So we have k here, which is wave number. 0. Yes, you are right. It will be 0. So why it will be 0?
Because k is 2 pi over lambda and 4 pi sinus is 0.
Yeah, exactly. If we have here lambda, we cancel it out. It will be 4 pi or any pi, sinus of any pi, it will be equal to 0. So you are right. This is equal to 0. Thus, we don't have this second term. We have only the first one, so we can write, so here we can delete this. We can write that the kinetic energy per one valence will be equal to 1 force mu omega square A square times lambda. So if we do the same, actually similar analysis for the potential energy, we will end up with the same equation. So potential energy U lambda per unit valence will be 1 force mu omega square A square times lambda. Now, if we consider total energy, which is per unit wavelength, E lambda will be equal to K lambda plus U lambda. Then we will get just twice more because they're the same. Will be 1/2 mu times omega square times A square times lambda. So that is total energy at any given moment of time. We considered specifically like t equals 0 per one wavelength. However, that is not the most convenient form for considering energy transferred by waves, and it's much more convenient to consider power, means energy transferred by wave per unit time. So now we deal with energy per one wavelength. We know that wave travels distance of one wavelength per time interval, which is equal to period of wave, t, capital T. That's why if we divide, so this power can be expressed as E lambda divided by period T. So this means that along axis X in the direction of wave propagation, this energy, which is accumulated, kind of like concentrated in the one interval of one wavelength, will move distance of one wavelength along axis X per time T, which is period. So means that per unit, that will give us energy transferred along axis X in the direction of wave propagation per unit time. So that will be 1/2 times mu times omega square times A square lambda divided by T. When we were considering in previous lectures these main parameters of waves, there was some relationship between these parameters and the speed of wave propagation. So as you remember, we were writing that V is equal to frequency times lambda, and which means that how many wavelengths per unit of time can be transferred, because frequency gives us number of wavelengths per unit of time. So that is equal, also frequency can be expressed as 1 over t, the period, times lambda. So that is exactly what we have here. That's why we can express this in terms of speed of wave propagation. So we can write 1/2 times mu times omega square a square times v. So this is the most important equation for our today's consideration. Means it quantifies how much energy per unit time, means hour, is transferred by the wave. So let us look at these parameters which are included in this equation. So first we have this mu, linear density. Obviously, if we have heavier string with all other parameters the same, we will transfer more energy. Then we have two most influential parameters because they are in second power, angular frequency and amplitude. So both in second power. Power of wave increases proportional to omega and a in second power, means that small change in these parameters will result the most in the change of the power transferred by the wave. So, and one more is speed of wave propagation. Obviously, if it moves through the medium faster, then it will transfer more energy per unit time. If we deal with a wave which is spreading in a different, with the same parameters, but different medium, I mean, same parameters and omega and amplitude, but in different medium, where speed is lower, so energy transfer per unit time will be smaller. So this equation should remember because that's quite common to use in some solving some problems for transfer, so for power of, or in other words, energy transfer per unit time by a wave. So summarizing our today's discussion, we considered, let's come back here, we considered some simple harmonic oscillator, which will result in a sinusoidal wave in our string, which is considered. So we have some small element of the string with the length dx, which we are interested in its kinetic energy. And then based on the expression for kinetic energy, we substituted mass by product of linear density and dx, velocity, this speed of wave propagation was substituted by equation which we derived earlier from the wave function, first partial derivative of wave function over time, assuming that x is constant. And then we integrated this expression in the interval from 0 to lambda in order to get energy, kinetic energy, which is represented by one wavelength in the interval of one wavelength. Then we added another half, which is originated from the potential energy per one wavelength, we achieve the total energy associated with this single wavelength, and then divided this total energy per one wavelength by time, which is period of wavelengths, and finally get with the substitution of lambda divided by t. We use velocity instead of this ratio. We get the final expression for energy transferred by wave per unit time, which is proportional to linear density, angular frequency in second power, amplitude in second power, and speed of wave propagation. Okay, so that is everything what I wanted to discuss during this lecture. If you have any questions, you're welcome. We will continue our discussions already about new topic, which is sound waves, kind of still related, but it will be focused more on features of sound waves next week. So I wish you good weekend. Take care and see you on Monday.
Thank you. Goodbye.
Goodbye.
Thank you.
Bye-bye.
Bye.
Goodbye.
Take care. Have a good day and weekend. Bye-bye.